Welcome back to a new episode on my exercise series Introduction to Physics. For the last videos we've been focusing solely on the effect of point masses, and we've been talking about how if we approximate some car or some person, some stone being thrown, anything literally, as some point mass, how do they then move? What about their energies, the conservation of momentum? But of course, in reality, everything around us is basically a rigid body. So today we are starting with the effect that we have to take into account if we are considering actually rigid bodies. So without further ado, let's start. For an art project, several wooden cubes with the density of ρ equals 700 kilograms per meters cubed have been installed. As a final act, the largest cube, with an edge length of 2 meters, should be turned around the lower left edge with a rope attached to the upper right edge. The rope pulls at an angle of 20 degrees with respect to the horizontal. How large is the force required? From this, we can take the following variables and values. First of all, we have given the density of the wood with ρ equals 700 kilograms per meters cubed. We have given the edge length A with 2 meters and the angle at 20 degrees. And we are searching for the force that we need to apply in order to actually turn the cube around. What does it look like? Well, let's have a look here shortly at this sketch. You can see this sketch of a wooden cube, and yes, it's just a side view. And on the lower left corner you can see actually that I marked the turning edge. And we want to pull at the upper right edge in order to turn it to the left. And of course this can only be achieved when we pull to the left hand side, not to the right hand side. So we know that the force points left and there is an angle of 20 degrees between this force and the horizontal. And we have given also this edge length. How do we calculate now the size of the force, the intensity? Well, what we know is that we want to turn it left, there will be some torque. And indeed, two different types of torque. First of all, there is this left turning torque. And in general, the torque, this kind of momentum M, let's give it an index L, equals F times L. So the force multiplied with the lever arm. Now, what is a lever arm? A lever arm is the perpendicular distance from the axis of rotation to the line of action of the force. And in order to make this more clear, let's make another short sketch. And you can see it here. We have the force F, and then there is this perpendicular distance that goes through our turning point T and hits F, the vector F, at an angle of 90 degrees at some point. And this is exactly the lever arm that we are looking for. Can we calculate it? Well, yes. If we think about it, we do have a triangle with an angle of 90 degrees. And yes, I'm talking about this one here, shaded in blue. There is the distance L. We do have given the value alpha, which is actually the same alpha that we have between the force and the horizontal. And, well, we need an additional expression, which is actually A plus X. Well, yes, this doesn't really help us, does it? Because, we can calculate the cosine of alpha as L divided by A plus X, but we wanted to get L in order to calculate our left turning torque, and now we've substituted the unknown value L by the unknown value X. So no, this doesn't really help us, but what if we also substitute X? Because, there is another triangle if you look closely. you can see it right here, shaded again in blue, we do have another triangle which has an angle of 90 degrees. And it contains actually x and alpha in such a way that the tangents of alpha equals x divided by the edge length a. And now this actually helps us because we can calculate x from the given variables a and alpha. So let's put everything together. We've seen that we can calculate the cosine of alpha as a function of L, a and x. We want to have L. So L is a product of a plus x multiplied with cosine of alpha. And we said that the tangents of alpha equals x divided by a. If we write this as x equals a multiplied with the tangents of alpha, then we have one equation that fits all. The left turning torque ml equals f multiplied with a plus a times tangents alpha and everything also multiplied with the cosine of alpha. We can again rewrite it in a simply nicer form shown here. So what we actually wanted to calculate was the force F, so we can put the force on the left-hand side and everything else on the right-hand side. Now we do have a small problem, because we do not actually have ml. What is it? Well, for a second, let's put it aside. Because yes, when we pull under a certain force F, the cube to the left-hand side, it turns. But if we let go, there will be a clear rotation to the right-hand side. So apparently there is also a right turning torque. And in general, mr can be calculated just as ml. It's force multiplied with the lever arm. But in this case, what are force and lever arm? Well, the force that makes our cube turn right again is simply the gravitational force. So F equals g, and we can calculate this as the product of mass m of the cube multiplied with the gravitational constant. And no, m wasn't given, but we do have the density. And mass m can actually be calculated as the volume V multiplied with the density ρ. The volume V? Well, again, it's not directly given, but it's a cube and we have given the edge lengths. So it's pretty simple. We know that in total the gravitational force equals a to the power of 3 multiplied with the density ρ and also multiplied with the gravitational constant g. So we can actually calculate this force in this case. Then we need in addition still the lever arm. So what is it? Again, let's make a little sketch. And we can see that when the force is the gravitational force and it just points downwards, starting basically from the middle of our cube, then the lever arm that has to have a 90-degree angle with respect to the force and has to go through the turning point equals a divided by 2. Half of the edge length. And this actually makes the calculation of the right turning torque very simple. But we know that our cube should not tip over. So basically it means that when we pull to the left turning torque has to be identical to the right turning torque. Hence, ml equals mr. And now this is pretty neat because we can just take our two equations that we have derived and we put the left turning torque considering the force F that we are looking for, the edge length and the angle alpha on the left hand side, and on the right hand side we have again edge length, density and gravitational constant. And we can calculate F then as a neat function of all given variables. Now, yes, when we look closely we see that we could basically put our given values into this equation, but personally I don't like leaving it at this. we can still simplify this equation, and what we get is that a to the power of 3 times rho times g divided by 2 and divided by the sum of cosine alpha and sine alpha equals f. And now we can take all our given variables and put them right here. And what we get is that the force is 21,430.7 Newton, which is 21.4 kilonewton. Now, of course, an angle of 20 degrees is not an optimum, not at all. And we see we are getting a really large force that we have to apply. And what happens if we actually choose a different angle? In order to turn our cube to the left, we could pull at an angle of 0 degrees, or we could also pull at an angle of 90 degrees, literally pulling it up. But if we think about it and if we actually calculate it, there is only one optimum between 0 degrees and 90 degrees, which is precisely at 45 degrees. And my question for today is, can you tell me why 45 degrees is the best? Meaning why we're getting the smallest force when we pull our cube at 45 degrees? Let me know in the comments below. And with this, I would like to thank you for your kind attention, and I hope to see you soon for the next video. Bye!